Good evening, everyone. So today we shall start the fourth week. We shall start with the fourth week lectures on special concrete. So basically, we will study on the effect of thermal stresses on the thermal stresses and heat of hydration on the behavior of concrete, and thereafter we will study two special type of concretes, which is the concrete underwater and the roller compacted concrete, also called RCC. So in the case of underwater concrete, we will be going through three types of concrete. Basically, ordinary underwater concrete, anti-washout concrete, and marine concrete. So yeah, so let us start then. So initially we will go through how the heat of hydration in cement and thermal stresses affect the concrete behavior. Okay. So yeah. So if we see the OPC composition from basics, if we see like the clinkers, they mainly compose of four compounds, also known as Bock compounds, and apart from that, there is gypsum addition for delayed setting. So this is the case of OPC, where we will find that alite contains about 45 to 75% of the total composition of the binder, which is followed by the belite, about 7 to 32%. Thereafter, that salite is there, 0 to 13%, and then phthalite, 0 to 18%, and last, 2 to 10% gypsum is added, as I told, for the late setting. If you see here, we will find that C3A, that is the tricalcium aluminate or the salite, it accounts for the largest, Hill evolution of heat, the compound which evolves the maximum heat, which is followed by halite and phthalite, and finally belite. So as you can see, so the C3S hydrates and hardens rapidly, and it is largely responsible for the initial setting in early string, as we have studied in undergrad. So the belite hydrates and hardens slowly and is largely responsible for the strength increase after 1 week. So if we see the plot between the rate of heat evolution and time hours, okay, so we will find that initially the rate of hydration is very high, and that is mainly for, as we just studied, for the hydration of C3A and C3S compounds. Okay, so that is less than 15 minutes. Okay, so from 0 to 15 minutes, the rate of heat evolution is the most. Okay, then very rapidly it starts to decrease. Okay, and decrease, and it is at minimum. Okay, at 2 to 4 hours because of the initial setting. Okay, so initial setting, when the stiffness starts to occur, the rate of heat evolution reduces. Then again it gradually increases, that is around 10 hours, okay, when the strength development starts. So that is mainly because of the development of secondary C3S hydration products. Okay, that is after 10 hours. And then there is again gradual decrease with a slight hump due to the secondary C3A hydration, which is around 30 to 40 hours. So all this is in the first week. Okay, so then it again gradually decreases, there is a decline, and after that the heat of hydration will only come after 1 week, when the belite phase starts to hydrate. So hydration of cement, as we all know, is a highly exothermic reaction. The heat liberated causes the temperature of the concrete to rise unless that heat is somehow removed. The concrete that is cast against formwork, very often we have leaves of concrete where a fresh batch is placed against another. This is a normal procedure. Okay, previously placed concrete layer. So it is placed one after the other. The strength development in concrete is a gradual process and is intrinsically linked to the hydration of cement. Thus, the concrete properties at early ages change very rapidly. So, if we see these two sketches now, let us understand to understand a little more deep. So let us see this, observe these two sketches. So this left side is a block, okay, and the right side is a slab, as you can see here. So if you see, you will find that this block has a lower area is to volume ratio, and this one slab has a higher area to volume ratio. Area basically is the surface area. Okay, any surface area if you consider, we will find that this is having a like the this surface areas, basically if we consider, it will have a more area to volume ratio as compared to this one. So if the same amount of heat is liberated in these two cases, it will be easier and easier removed, okay, from the large surface area of the slab as compared to the block, okay, because more is the area for the liberation of heat, okay, so larger will be the amount of heat liberated. So given the geometry, the thermal temperature gradient in block, this one will be more severe in the than in the slab, because in this case the heat of the amount of heat liberation will be less, so therefore the thermal gradient will be very high, okay, as compared to this slab. So if we take a illustrative example to understand even further better, so let us consider two like both like two shapes, okay, one is a cube and one is a slab, where the cube is both are having the same volume, okay, while the dimension of the cube is 2 meter each side, and the slab is having a surface of lateral dimension of 6.3 by 6.3 meter and a thickness of 0.2 meter or 200 mm. So if we see that this the block basically has a surface area of 24 meter square, whereas the slab is having a surface area of 84.4 meter square, just because of its dimensions, although the volume is same. And if you go into it, if we want to further specify, we will find that there is one surface area at the bottom, that is 4 meter square, one up exposed to atmosphere 4, and the sides are having formwork atmosphere contact of 16 meter square, while here we will see that the top and bottom is having the maximum, that is 36.7 meter square each, while the four faces contact with formwork and atmosphere sides are having just 5.04 meter square. So as we can see here, we will find that it is almost 9 times more, okay, so the amount of heat that is liberated will also be 9 times more. So from this we come to the definition of what is mass concrete, okay, so this is a special concrete which we are going to discuss after this lecture. So mass concrete according to American Concrete Institute is basically defined as any volume of concrete, okay, which is large enough to require measures to be taken to cope with the generation of heat from the hydration of cement and attendant volume change to minimize cracking. So mass concrete is basically any concrete, okay, which is so large that it requires various measures to be taken for for taking care of the heat generation, okay, for reducing the amount of heat generation due to hydration, as well as to minimize the cracking occurring due to the volume change, okay, basically for the cracking shrinkage conditions, okay. So all those happening mainly because of hydration, generation of heat from hydration. So it involves pores of large volumes of concrete with relatively smaller surface area. So the best example will be gravity dams, okay, so dams which act due to its weight, okay, whose capability is on account of its weight, okay, which preserves water, okay, which stores water and which resists water movement from due to the moment generated due to its weight. So the gravity dams can be cited as an example of such construction. And even medium pores, okay, of high strength concrete such as piers or anchorages, which are used in bridges, so made with high strength concrete with a high cement content, so they could also qualify as mass concrete, okay. So any huge amount of pores where the generation of heat is a concern can be defined as a mass concrete. So the characteristic feature of mass concrete that differentiates its behavior from that of structural concrete is its thermal behaviors, just as we studied just now. So the main characterization, the main differentiation factor of the mass concrete with that of structural concrete is the thermal behavior property, okay? Because in structural concrete, the heat generated by the hydrating cement is rapidly dissipated, okay, and it is only slight there is only slight temperature difference development, okay, which is not the case in mass concrete, okay. So that is basically the difference. So what are the factors which affect the temperature rise? So basically there are four factors. So first, as we all know, is a cement composition, that is the cement should have as low as possible C3S and C3A, because these give the initial hydration and the heat generation, okay. So most mass concrete structure do not need early edge strength because of this criteria, because of the temperature criteria. So slower hydration is usually not harmful to construction. So as low it will be, So there will be low amount of stress, thermal stress and tensile stress development, and also the working environment will be much higher, good, much superior for the laborers. Second is the second factor affecting temperature is the cement fineness. So as we all know, more will be the fineness, that is lesser the size of the cement particle, more will be the rate of hydration. Okay, so if we have lower fineness, that is if we increase the amount of size, okay, or increase the roughness, so what will happen, the amount of hydration will be slow. Okay, so slow is the hydration, so less will be the heat liberation. Okay, so lower fineness is therefore useful. Cement content should be as low as possible, from say for 100 from 100 to 120 kg per meter cube, and the geometry, just as we just studied, it should have a large volume surface area ratio. It should have a small volume surface area ratio, because if it is having a large volume surface area ratio, that is having a smaller surface area value, then that is more susceptible to thermal cracking. Okay, so therefore the pore should have a small volume to surface area ratio. So taking into account all these factors, what we will find is that the concrete should have a MSA, that is a mean size of the aggregate, around 150 mm. So bigger is the aggregate, as you can see here, it's better. Okay, and secondly, a high, because less amount of cement will be thereafter required. A higher coarse aggregate content, that is about 70 to 80%, can be used. That will lower the cement content and reduce the temperature rise, just as we just as I stated. So therefore, larger MSA, mean size aggregate, plus better packing, okay, that will generate less amount of heat, as you can see this case. Okay, so depending upon the geometry of the member or portion of the concrete being cast, the temperature of the core of a large concrete block will be higher than portions closer to the surface. Okay, so that is very simple, trivial. So as we because more will be the surface, greater will be the generation of liberation of heat, so lesser will be the temperature. So the difference in temperature in the core and portion close to surface sets up thermal gradients, which are the root of mass concrete related issues. So the main mass concrete issue, which separates it from structural concrete, is the issue of thermal gradient, because it involves a lot of amount of cement, because it is mass. Okay, mass concrete. So what is thermal stress? Thermal stress is basically generated in concrete on account of shrinkage and volume changes related to release of heat of hydration of cement. Okay, so basically it is the shrinkage and volume changes occurring mainly due to heat release due to hydration of cement. Okay, so if the surface temperature is allowed to deviate greatly from that of the core, thermal cracking will develop. Okay, so most codes therefore require a temperature differential of less than 30 degree to 36 degrees centigrade from the surface to the core of the section. So the difference between surface to core should be less than 30 to 36 degree ideally, as per the most codes. Okay, and secondly, when the thermal cracking will occur, that will occur when the thermal stress, okay, that is the tensile stress which is generated due to increase in temperature, will be greater than the tensile strength of concrete. Then only the thermal cracking phenomenon will occur. So let us go more deep into that. So say for example, we have a concrete block, okay, which is having a original length L, okay, and after after here temperature rise of the block due to cement hydration, there is expansion, okay, in the block. So here in this case we have kept the base as glass, okay, because glass does not provide any friction, okay, so it will not impact the phenomenon in any way. Okay, the base will not have any impact, so early age concrete is easily able to deform. Okay, so what we will see is that upon cooling, the concrete wants to this concrete block, due to heat generation, it started to increase, okay, and expanded this much. Okay, but after cooling, it tried to reduce, okay, but it was not possible to come back to its original shape. Okay, so after contraction, the length became in between the original and the expanded length. Okay, so this was the final length after contraction. So upon cooling, the concrete wants to come back to its original position, but this contraction is resisted and the concrete finally reaches an intermediate position. Okay, so now if this tensile stress exceeds the tensile strength of the concrete, it will crack, just as we studied. Okay, so as you can see in this photograph, so there is high core temperature inside, and cool surface outside. Okay, but when there is this high degree restraint, okay, so that will generate the tensile stress, and that will lead to the thermal cracking. Okay, so when dimensions are greater than 1 meter, temperature rise should be therefore considered. Okay, that will happen in mass concrete. Mass concrete does not apply to large dams, but also to any large pores. Okay, so any pouring, concrete pouring, which is having any dimension greater than 1 meter. Okay, so that will be considered as a mass concreting, and there the temperature rise should be a primary concern. So if we see in this sketch, okay, so we will find this is the initial condition, that is the specimen having an original length of L. Okay, so by temperature rise, if there is no strain involved, it can expand to this it can expand this much. Okay, so free deformation. Okay, because as the degree of restraint is 0. But when there is restrained strain, okay, so this is, if it is not allowed, okay, this is completely restrained, so then the thermal stresses will develop. Okay, and if that is greater than the tensile strength, so then cracks will appear. Okay, if there is like as we saw in this example, so if there is allowable, little bit allowed, okay, little bit strain is allowed, but this much is restrained. Okay, so this is around 0.3. Okay, so we will find that the amount of restrained strain will be 0.3 into free strain. Okay, so that is the basically the condition of partial restraint. So these phenomena are occurring because as the temperature in the surface and the core, okay, are not equal, so the the ability of deformation of the two areas will not be same. Okay, so because it will not be same, there will be some kind of restraint development, and if that restraint development is creating a tensile stress which is greater than the tensile strength of the concrete, so then the cracks will occur, which is called the thermal cracks. Okay, so simplistically speaking, the problem of thermal stresses in concrete can be studied by integrating all the three factors. Okay, so that is the heat generation or the liberation of heat, the movement of heat through concrete through the thermal gradient, and the dissipation of heat to the atmosphere. So these three together, the will together combine to form the problem of thermal stresses. Okay, so all these three can be useful for studying and finding the solution. Okay, so there these are the parameters, okay, so which can be considered, which can be influenced, okay, to find a solution. So one is the volume of concrete. Okay, just as we studied, same volume but different surface area can be useful. Proportions and properties of materials used in the concrete. So as we just studied, if we increase the concrete size and decrease the cement content, or we add some kind of admixture, so that can be useful. A special importance is the properties, fineness and composition of the cement. So just as we studied, if we can increase the if we reduce the fineness or increase the size, okay, that can be useful. And fourthly, unit cement content. Okay, so lesser is the cement content, as we just studied, 100 to 120 kg per meter. So lesser the better. Okay, so for pores with complex geometries, computer models are also nowadays used. So genetic algorithms are also used to model cement hydration to predict temperature distributions. Okay, so adiabatic temperature rise, as you can see here, can be used for a conservative estimate. So it is a conservative adiabatic use can give a conservative estimate because this is a pessimistic. Okay, it is much higher than the actual case. Okay, but if we take as a if we take it as a factor of safety, so we can have a proper design which is conservative. Okay, so as we can see here, with age there is a plot of temperature rise. So if we see adiabatic, where that means there is no change, there is no transfer of heat, loss of heat, so it has the maximum temperature rise. The natural cooling, okay, so there is increase but it gradually decreases. In artificial cooling case, okay, the temperature rise is lesser, and there is faster cooling. Okay, and from this we can find that the temperature rise in actual, okay, this one is lesser than the temperature rise in adiabatic. That's why it is a conservative estimate. Okay, and due to that is mainly because there is heat flow to the surface in the case of natural cooling. Okay, that is not possible in adiabatic because the temperature increase of the concrete, okay, is maintained with the temperature increase with in the surroundings. Okay, the surrounding temperature and the concrete temperature is increased, due to which there is no loss of heat. Okay, so therefore the adiabatic condition Q is equal to 0. So if we, if we plot this, okay, if we like few investigations research have found that if we go further, this plot, if we see, there will be various if this is actually the behavior almost similar is the cases for different some criteria. Okay, so if you idealize this, okay, idealize and plot it into an idealized curve, we will find that after T placement it will have a sharp increase to a temperature of T max. Okay, and then it will slightly gradually decrease to the temperature of T ambient. Okay, and then it will become saturated. Okay, so there will be no increase or decrease. So this temperature difference between T max and T ambient, it is called the delta T. So the placement temperature is also therefore a important factor. Okay, so it has been found that pouring at low temperatures will reduce the thermal stresses in this section. So as you can see, from 0, every every temperature for different temperature conditions, the heat of hydration, because of heat of hydration, the temperature rise is seen. Okay, but if we see the working condition, the condition where 10 degrees centigrade is used, temperature rises minimum, and where 30 degrees centigrade is possible present, temperature rises maximum. Okay, so that means, if firstly, if there is slow hydration. Okay, so if there is slow hydration, it will lower the heat of hydration. Okay, so slows the placement temperature slows hydration. Okay, and that will result in lowering of heat of hydration. Okay, and secondly, lower temperature differential between the core and the outer surface. So that is, uh, as you can see, lower temperature differential between the core and outer surface. So because the placement temperature is low, okay, so that will lower the differential. Okay, and that will result in lesser gradient. Okay, and apart from that, one more important thing is the volume to surface ratio, as we just studied. Okay, so here, as you can see, if the surface ratio is maximum, okay, so this ratio will be minimum. So minimum, that more is the surface ratio, more is the surface area, so lesser will be the temperature rise. So, and lesser is the surface, more will be the temperature rise. So it is a upward parabolic. Okay, so lower ambient temperatures produce less temperature rise, and lower volume surface area ratio produce less temperature rise, as you can see here and here. Okay, so properties of concrete such as conductivity, specificity, diffusivity, and the coefficient of thermal expansion of concrete. So these are the important parameters which is related to aggregate properties and proportion. Okay. Temperature difference between neighboring concrete elements between the core part and the surface could be an extreme example. So if we see here the thermal gradient, okay, so occurs from or through the surfaces, as we know. So it will be different for the bottom, okay, for the top surface and for the walls. Okay, it is because bottom is cast against earth or pervious concrete. Okay, so there we have to find the properties of the earth or soil or some concrete layer beneath it. Okay, in the walls there will be formwork, okay, which will be again connected to the atmosphere. Okay, but in the top surface it is directly exposed to the atmosphere. So all the three will have different thermal gradient value. Okay, so significance of curing practices to be borne in mind, because in formwork, formwork is basically for the curing purpose. So for different formwork application, the walls will have different thermal gradients. Okay, the surface area and surface temperature of concrete through which the heat is transferred to the atmosphere, as we studied. Temperature difference between the concrete and the atmosphere, and the conditions of the atmosphere can be wind, rain, high temperature, low temperature, etc. Okay, we studied the high temperature, low temperature concrete in the last class. So therefore, what is advisable is that every possible trick that helps lower the peak temperature should therefore be explored. As we studied, the cement content should be reduced. Okay, it should be reduced to 100 or 120 kg per meter cube. This can be achieved through use of chemical admixtures, air entrainers, or simply increasing the water cement ratio. The strength of concrete would be about 12 to 15 megapascal, which may be acceptable. Okay, replacing a part of cement by materials such as fly ash, okay, that can be also encouraged. using low heat of hydration cement. Okay, this could have different meanings for concrete in dams and high strength concrete. Okay, so characteristics will be changing due to environmental conditions and various other factors. So using chilled water or ice flakes with mixing water can also be a good alternative. Okay, using maximum possible size of aggregate, as we just studied, for reducing the water demand as well as cement. Okay, and thereby reducing the unit water content, which in turn reduces the unit cement content. Okay, so that is a good option. Arriving at a most desirable combination of coarse aggregate sizes, that is the gradation, in order to achieve effective packing. Okay, so that is also required for achieving a proper packing. So desirable combinations would also be important, is also important. Studying carefully the aggregate mineralogy is important. These and the aggregate content affect the properties such as elastic modulus of concrete, which is an important factor in determining the actual tensile stress in concrete. Okay, so we all know the importance of elastic modulus. Other properties such as heat diffusivity and coefficient of thermal expansion are also greatly influenced by the aggregate properties. Okay, so because they are present at about 70 to 80% in the entire concrete, so their properties will indirectly affect the properties of the main concrete. Okay, so use of concrete of the stiffest, using concrete of the stiffest possible consistency. So lesser the consistency, it is better. Okay, sorry, lesser is the slump, it is better. In fact, given the volumes of concrete involved, alternative methods of placing and compaction should be considered rather than increasing water content. Okay, because increasing water content is good, but that will also result in increasing the cement content. Okay, so therefore lesser is the water, okay, more is the stiffness, so lesser will be the cement content required. So that is an good thing. Okay, this is a that is the best option. Okay, that is the most suitable option to facilitate construction. So how, now the question is how to lower the peak temperature. Okay, so for lowering the peak temperature, there are basically two ways. Okay, one is pre-cooling, one is post-cooling. Okay, so pre-cooling, basically it is, pre-cooling is done in materials. Okay, so pre-cooling is done in materials, that is the material composition to material constituents to lower the placing temperature. And post-cooling is done through a network of pipes buried in concrete which run cold water. Okay, so in order to remove the heat generated and reduce temperature rise. Okay, so as you can see, pre-cooling of materials was first used in the Norfolk dam. Okay, so in this dam construction in the early 1940s, pre-cooling materials were used, and the post-cooling method was initiated earlier than that, in the earlier than pre-cooling, and that was first used in the Hoover Dam. Okay, in United States in the early 1930s. Okay, so placing temperature is related to the temperature and proportions of the different materials. Okay, so let us go more deep into pre-cooling. So pre-cooling involves use of pre-cooled materials with the intention of lowering the initial placement temperature of concrete. Okay, this also has the advantage of reducing the water demand, which is related to the temperature of placing being lower at lower temperatures. Okay, so for this, what we can do is we can adopt two ways. One is using crushed ice or chilled water as mixing water, and second is by using cooled aggregate. Okay, so need to set up special facilities for pre-cooling materials and lower the temperature to say 5 degree to 7 degree centigrade. Okay, so using these methods we can lower the concrete the material temperature to 5 to 7 degree centigrade. Okay, so that is a good thing, good way, alternative. So water has a higher specific heat than rock aggregates. Okay, it has been found, and therefore it is more efficient to use chill water than chilling aggregates. Okay, so because higher, it is a higher specific heat. Okay, so if we reduce the temperature of water, okay, so the temperature, the effect, okay, the effect will be more profound. Okay, so like the effect will be less profound, the high temperature effect will be less profound because water is having a more specific heat, so it's better to use chilling water. Okay, so carrying this thought forward, use of ISO is most efficient. Okay, and aggregates may be sprayed with chilled water before use. Okay, so that can be done. So both ways, using water. Okay, so it can even cool water, and that water can even be sprayed to aggregates for cooling the even aggregates. Okay, so by one, by one way you are doing all both the ways. Okay, so that is a good thing. Okay, and then that is the pre-cooling way. Okay, so let us now go to the post-cooling. Okay, so that is achieved through circulation. As we just studied, post-cooling is basically a network of pipes which runs cold water. Okay, after casting of concrete. So this is achieved through circulation of cold water in pipes which are about 25 mm in diameter and 1.5 mm wall thickness embedded in concrete. Okay, so they are helpful for stabilizing volumes of concrete so that other operations such as grouting at joints etc. can be done to ensure monolithic behavior. Okay, so this is important, okay, to avoid the cold joints. Okay, so there is no segregation of layers of concrete. Okay, so this helps concrete to you come to equilibrium much faster. Due to the low conductivity, it may take several years to achieve otherwise. Okay, so as you know, for reaching the thermal stability, okay, as the conductivity is low, okay, so if we can reduce the temperature, cool as fast possible, okay, so it will take less time to reach the stability. But as it is having low conductivity, if we don't employ all those techniques, so it may take very large amount of years, okay, to achieve, okay, the thermal stability, as we will see later in a slide. So when should the water circulation be started and at what rate? So okay, so this is the question which is of research importance. Okay, and it will be different for different scenarios. Okay, so the best way will be to do some trial, okay, trial mixes and trial, trial tests, okay, before the actual construction of a mass concreting structure. Okay, so the rate of heat removal is obviously related to the flow rate of cold water in the pipes. This needs to be carefully designed for the entire period. Initially, when the modulus of the concrete is low, the heat removal can be as quick as possible. Okay. Strength and modulus of elasticity increase quickly after the peak temperature is reached, which may happen during the first 2 weeks. In the stage that the concrete is elastic, the rate of cooling needs to be controlled to avoid adverse effects and allow for stress relaxation. Okay, so these are the factors points which needs to be kept in mind. Okay, some possible too much cooling and like freezing and thawing type of thing will not be a good option. Okay, so because concrete is brittle, that may adversely affect the performance. Okay, so some possible design and quality control specifications, few specifications which can be given is one, a cap on the maximum acceptable temperature for individual materials. Okay, so that can reduce the temperature. Second is the cap on the maximum placement temperature, okay, using this pre-cooling, post-cooling techniques. Thirdly, using the extent of temperature rise and subsequent drop, okay, can be a design parameter, just as I told you, in the design of structures where heat of hydration is suspected to be an issue. Okay, a value such as 30 degrees centigrade could be one such example. Okay, so there should be not a much difference, temperature difference, as we studied early. So as less difference possible will be a better better situation for the concrete. Okay, the peak temperature reached can be another design parameter. Okay, a value such as 50 degrees centigrade could be one such example. And accounting all this, a thermal cracking index, okay, TCI, can be another such parameter. Okay, so these are some of the ways and specifications which can help in design and quality control. Okay, so now let us see what is thermal cracking index, TCI. Okay, TCI is basically the ratio of tensile strength, okay, and a maximum tensile stress of concrete. So tensile strength is basically the strength of concrete, and tensile stress, okay, that is basically the thermal stress generated in the concrete due to the condition. Thus higher the TCI, the better it is. Okay, because more will be the strength of concrete, so better, higher will be the TCI value, and that is a good thing. The tensile strength, for the purpose of calculating the TCI, can be taken to be at the time the peak thermal stress occurs. Okay, so because there is a variation of the strength. Okay, so it's better to take the tensile strength, okay, uh, which is at the time the peak thermal stress occurs. Okay, so it should be uh, equivalent. Okay, it should be at that time equivalent where the peak thermal stress occurs. Okay, so the TCI is time dependent and hence needs to be calculated at different ages, just as we discussed. So as you can see here, this is a plot between thermal cracking probability and thermal cracking index. Okay, so this has been given in JCI, that is Japan Concrete Institute. So for guidelines for control of cracking of mass concrete 2008. So as can be as it is self-explanatory. So higher will be the thermal cracking index, that is greater will be the strength, okay, of concrete, tensile strength. So lower will be the thermal cracking probability, okay. So more is the strength, lesser is the cracking probability. And for design parameters, it is considered the thermal cracking probability should be taken as 5%, okay, and that is equivalent to a thermal cracking index of 1.85, okay. So in general cases, limit value of thermal cracking probability is given as 5% when the structure is required to be crack free, okay. Even more optimism is required in the design. A limit value lower than 5% needs to be specified, okay. But if the structure is not of that importance, okay, or when a higher risk for cracking is acceptable, okay, a value more than 5% can be allowed, okay. So that will depend upon the seriousness or the importance of the structure, okay. It should be noted that the tensile strength of concrete varies and only develops over time, and therefore a value based on a parameter such as a characteristic strength cannot be used, okay, because it changes over time, okay. So we cannot be we can't have a certain value, okay. So therefore at the time the peak stress occurs, for that given stress given time, what is the peak tensile strength, so that is generally considered, okay. So what are the applications of large pores, as we discussed briefly? So we have found that large mass concreting or large pores are used in dams, massive foundations, bridge piers, okay, anchors were also there, thick slabs, nuclear plants, structural columns. So all involve large pores, okay, with little small differences, but all come in the category of large pores, okay. Now as I told you a few slides back, the issue of thermal stability, why it is important and why the temperature should be low. It is because thickness, if a thick concrete wall is 0.15 meter, okay, so it will become thermally stable after 1.5 years 1.5 hours, okay. But if it is having a thickness of 1.5 meter, it will take week, okay, it will require a week. So it is almost it is almost almost 100 times more, okay. So then if the thickness of the wall is 15 meter, say for example in arch dam, so it will require 2 years, okay. And if the thickness of a wall is 152 meter, okay, so say for example in the case of Hoover Dam, it will take 200 years, okay, to achieve the same degree of thermal stability. So therefore lowering the temperature is of the materials by pre-cooling, post-cooling methods is very much important. So these are the few of the ways are being listed, which can help in tackling the high temperature conditions during mass concrete, okay. So one is the using lower cement content, okay, so that will reduce the amount of heat generated. Second is lowering water cement, okay, so low water will result in low cement, okay. So thirdly, using high water content, okay. Fourthly, using low fineness of cement, then higher aggregate content. So changing aggregate mineralogy, low C3A and C3S content in cement, higher C4AF and C2S content relative. So we have studied all this now. Adequate curing, pre-cooling ingredients in concrete, using cold water or ice in concrete, using liquid nitrogen, post-cooling methods, alternate methods of placing and compaction, use of fly ash and slag. So most of the ways we have discussed, okay, just now. So that is mainly about thermal stresses and how heat of hydration affects concrete, okay. Now let us go to the one of the special concretes, that is the underwater concrete, okay. So there let us study what is anti-washout underwater concrete. So this is basically a concrete structure which is in water, okay. So general view of the job site, and here you can see some construction going which is underwater. So here the divers are arranging the reinforced bars, okay. So in underwater, okay, so if we want to test fresh concrete underwater, so what, if you see, okay, so this is the initial shape, okay. So this is possibly the consistency test. So this is the initial shape, okay. After the the slump is allowed to flow, this has become the final shape. And you can see here it is the slump cone in water tank, and this is filled with water. So testing fresh concrete underwater, okay. So concrete should flow or deform in water. And if we see here, maybe they have tried to find out the compressive strength. So cubes have been cast. So collection of cubes underwater, demolded and allowed to remain there. So this way underwater testing can be done. So placement of high quality underwater concrete, leaving the marine life undisturbed. Okay, so that is the main criteria. Okay, so our main motto is firstly to place underwater concrete which is high quality, okay, without segregation, without bleeding. And secondly, there should be minimum or no undisturbance of the marine life. Okay, so if both of the objectives are satisfied, so then we can be we can say that we have achieved our purpose, okay, our objective mission. So here you can see here how the underwater concrete is being placed. So here they have used a pumping, okay, through pumping, they are machine pumping, they are trying to pour concrete, okay. So now let us see what is anti-washout concrete. So basically this concrete can be placed underwater in a similar manner than normal concrete, okay. How a normal concrete is placed in air, and it was initially developed by Germany, and then it was extensively researched and used in Japan. The concrete basically uses a viscosity agent, okay. So this agent is used in normal concrete, and that is used to address the segregation and bleeding issues which are associated with underwater, okay. So viscosity agent is the main criteria which segregates anti-washout concrete with normal concrete, and that is used to address segregation and bleeding. So what are the applications of anti-washout concrete? We can see that they can be used as bonding and solidifying rocks and concrete blocks in shore protection works. Okay, they can be used in as underwater reinforced concrete for constructing wharf, intake and discharge facilities for industrial plants. Okay, they can be used as alternative for precast concrete for constructing breakwater, QA wall, etc. So they can be used for those wall. QA wall is basically the dock wall, okay, where the ships are tied. Okay, bridge foundation, minor fixing works and emergency repairs, so it can be used for that. Maintenance works around underwater structures, it can be used for that. Construction and repair, shore protection, riverbed, water gate, etc. So all these are the applications of anti-washout concrete, underwater concrete, okay. So if we see in this representative diagram, so this is an example of normal mortar, okay, and this is the example of underwater anti-washout mortar. So what is the distinctive feature? The distinctive feature is that here there is, in this case, there is no segregation as can be seen here, and that is because of the viscosity agent, okay. And also there will be no bleeding, okay, because there is no segregation, okay. So the viscosity agent has to be added in some dosage, okay. So the standard dose is mainly between 1 to 1.3%, okay, but it can vary with various criteria or conditions, okay. And as you can see here, the if it is less than 1, what happens is it is erosion proof, the erosion or the segregation will occur, okay. So that's why it should be greater than 1. But if it is greater than 1.3, okay, then what happens is that it is okay, like there will be no segregation, but the material cost is very high, okay. So that will lead to uneconomy. So we have to be between it should not be uneconomical, as well as there should be no segregation. So in between economy and no segregation, we have to find the dosage, standard dosage. So as you can see here, this is a case of regular mortar, okay, which has been segregated, okay, and dispersed. So this is the mortar with a high dosage of viscosity, okay, agent around 1.3%, okay, and similar results have been obtained, okay, using a viscosity dosage of medium level, okay, medium dose. So that is 1%. So this is economical, okay. So this is the best, okay. So as I told you just now, so if you see, if you compare anti-washout concrete with underwater concrete, what we will see is that the material cost, okay, the material cost of anti-washout, basically the viscosity agent is very high, okay. So it is high, it is almost 3 times of the underwater normal ordinary underwater concrete, okay. But if you see the concreting cost, okay, so concreting cost is basically only it is 50% as compared to 90%, okay. So it is almost half, okay, half of the concreting cost. And because this is very less, okay, the total cost is also only 80% of the underwater concrete. Okay, so main factor is the concreting cost. Okay, so concreting cost is low. That is so low because we don't have to care about segregation and bleeding and all those criteria, because the chemical takes care of all of these factors. Okay, so that is the benefit. So if we now say, for example, for a particular case, if we want to see the compressive strength between air and underwater. Okay, underwater is mainly the anti-washout and air is the normal. Okay, so we have taken water cement ratio as 50%. We have taken the maximum size of aggregate as 25 and we have found out the compressive strength of 28 days. Okay, so we will see in irrespective of whether the aggregates are river gravel or crushed stone. Okay, we will see that the compressive strength of the anti-washout concrete is always higher than the standard concrete in air. Okay, the anti-washout concrete, which is cast in underwater, is always higher, having higher compressive strength as compared to ordinary concrete which is cast in air. Okay, so there lies its value. Okay, so and also it is the cost is also 80%, okay, of the actual of the ordinary concrete. So this these criterias we have to study. Okay, so what is the water type? Okay, is it still water, it is running water, what is the self compactability and segregation resistance? Okay, these are the factors based on which we have to design the anti washout dose. Okay, the viscosity agent dose. Methods of construction. Okay, there are basically three methods underwater: tremie, and this one machine pumping, and by buckets. Okay, so we will study all those now. Concrete always remains submerged in underwater, and development and use of specially designed anti-washout concrete. So that is the requirement. So here, for example, as you can see, this is a trial. Okay, the trial design. So here they needed concrete volume of 357 meter cube. Okay, so through mixed proportioning, they required specified compressive strength as 18 megapascal. The maximum size of coarse aggregate came to be 20 mm. The slump flow as 40 centimeter. Water cement ratio as 51.3%. The unit water content is 205 kg per meter cube, and the viscosity agent was taken as 1.5%. The W. Okay, so it came 3.1. If you remember, we discussed it should be between 1 to 1.3, but that is our standard. Okay, but here they have maybe they have taken some other cases, like for example, is the water still or running? Okay, or all those issues. So it can vary. Okay, there is no ideal value, but it should be between. Okay, it should not be unnecessarily high, and it should not be so less that there is erosion. Okay, so if in this case, if you see, you will find that for 246 meter cube concrete volume, they have applied mixed proportioning, and for a specified compressive strength of 21 megapascal, they have found that maximum size of coarse aggregate is 40 mm. The slump flow is 60 centimeter. The water cement content ratio is 54.7%. The unit water content is 208 kg per meter cube, and the viscosity agent has been taken as 1.2%, the W value, which is coming to be 2.5 kg per meter cube. So this is, as we saw in the chart, it is a very good value. Okay, between value. So materials, basically what type of materials are used in anti-washout concrete? The cement is normal cement. Okay, or it can be also blended cement, like using mineral admixtures. Okay, both can be used. Admixture, basically here they have specifically specified, they have specified especially the viscosity agent. Okay, which we have discussed till now so much. So that is mainly cellulose ethers. Okay, they provide highly erosion resistance, and the super plasticizer, as we all know, they reduce the water demand. The mixed proportioning, as we just studied, the viscosity agent doses range between 1 to 1.3%, but that is adjusted depending upon requirements such as height of fall through water, running or still water, etc. Just as we saw an example where the value came to be 1.5%. So consistency of anti-washout concrete. Okay, so this consistency will basically depend on two criteria. One is the placing method, and second is the placing condition. Okay, the placing method, as I just told you, it consists of three ways. Okay, one is concrete pumping, one is tremie pipe, and third is bucket. Okay, so we have studied tremie pipe last class also, and concrete pumping is basically pump. Okay, and bucket is, as we all know, like they bucket is bucket full of concrete will be will be uh, will be poured into will be taken in inside the water, okay, and dumped at the location, okay. So these are basically the methods of placement of anti-washout concrete and all types of underwater concrete. So and this is a criteria which depends which which affects the consistency. And second is the placing condition, okay. That is basically it can be of various ways how the concrete is placed. For the condition of placement, for example, the slope, general condition, reinforced concrete, filling narrow space, filling narrow and deep space. So all these factors, okay, all these factors come into this one come into picture, okay. So now the what happens is this is a table which shows the slump flow, okay, required for various structure conditions and placement methods, okay. So as you can see, bucket, tremie pipe and concrete pump all can be used in every structure condition, okay. But the slope and general condition can be used for 50-meter or less, okay, underwater height depth. And reinforced concrete structure, filling narrow space, filling narrow and deep space techniques conditions can be used for 50 to 200-meter this one water depth, okay. So for all the this one conditions, the slump flows values are mentioned, okay. So here is an example of mix, okay, mixed proportions, okay. So they have this one designed according to the needs, okay. So mixing, how it is done is dry materials have to be mixed initially for half a minute or 30 seconds, followed by more mixing of 1 minute 60 seconds after water addition. So it is complete total 1.5 minutes, where 0.5 minutes they have to mix dry, and after mixing water they have to mix 1 minute, okay. So total 1.5. So that is basically about anti-washout concrete, okay. So now that is one of the type of underwater concrete, okay. So now let us study the other two types, okay. One is this one, one as we just studied is anti-washout, the other will be the ordinary, okay, and the third will be the marine concrete, okay. So this as I just told, so ordinary underwater concrete, so what are basically the factors, the characteristics which are different is mixed proportions, placement, tremie, pumping, bottom discharge, buckets, bags. Anti-washout concrete we just studied, materials, mixed proportions, mixing, placement, protection of concrete surface, and marine concrete, all those, okay. These are the constituents, okay, they are the specifications. So if we go general, underwater concrete is constructed over a relatively wide area in the ocean or in other underwater areas. Also used for cast in place piles or diaphragm walls, okay, that involve the construction of reinforced or steel frame reinforced concrete in water or in stabilizing fluid. Ordinary underwater concrete is used mostly for unreinforced concrete, okay. Anti-washout underwater concrete with increased resistance to washout is used for unreinforced or reinforced concrete. So ordinary underwater is basically used for unreinforced. Anti-washout can be used both for unreinforced or reinforced, okay. So in case of ordinary underwater concrete, the underwater concrete cannot be compacted, as we all know, and so requires an appropriate amount of fluidity. Standard slump at the time of placement has been specified according to the construction method as per this one, JSC, Japan, Society of Civil Engineer. So basically Japan has done a lot of work in this field. So as you can see, construction method as per tremie pipes or concrete pumps, okay, the range of slump is around 13 to 18 centimeter, okay. But if the buckets are used, bottom discharge buckets, okay, or bags, okay, so if those are used, then the range of slump is 10 to 15 centimeter. So the highly cohesive mix proportions are required so as to minimize material segregation. Hence, appropriate admixtures and increasing the percentage of fine aggregate to an appropriate level are required, okay. So mainly the cohesive nature is important, okay, in order to minimize segregation. Standard percentage of fine aggregate should be set at 40 to 45% in cases where gravel is used for coarse aggregate, and should be increased 3 to 5% in cases where crushed stone is used, okay. So we have to give mix the keep in mind the design mix. We have to keep in mind the this one conditions and the this one constituents, and accordingly design our mix. So compressive strength of underwater concrete placed by tremie may sometimes be reduced to approximately 60% of compressive strength of a standard specimen if the distance of flow from the tremie exceeds 3 meter, okay. So if the depth is more, then it sometimes can reduce to 60% of the desired value of compressive strength. So this suggests that concrete is likely to be subjected to washout in the vicinity during underwater placement and have its strength reduced. In order to minimize strength reduction and result in concrete quality deterioration, and to ensure the ease of construction, rich mixes are desirable for underwater concrete, because there is a chance of loss. Okay, so better the mix, okay, richer is the mix, better is the better is the desirable value, okay, for underwater concrete. The standard mixing water cement ratio and minimum cement content have been set at 50% and 370 kg per meter cube respectively. So all these values are as per standard specification for concrete structure JSC 2007. Okay, so it should be all, the concrete should be placed while building an appropriate temporary enclosure. Okay, that is basically the tremie way. Okay, to control the flow of water to prevent water contamination due to the washout of uh, this one cement and the formation of latents. So segregation and latents and washout, these are some of the some of the important issues associated with underwater concrete. Okay, if no complete enclosure can be built, concrete should be, that is if the tremie is not possible, concrete should be placed with while the flow velocity is 5 centimeter per second or lower. So that this is one of a this is a standard value. Okay, so the flow should be as low as possible, and the criteria is it should be less than 5 centimeter per second. Okay, either this or lesser than this. So letting concrete fall in water causes material segregation, okay, and washout of cement, because water will give pressure. Okay, as per the Pascal's law or any law, as you can see, it will give force in all the directions. Okay, so that will lead to segregation and washout. Surface latents shall be removed at the end of placement of a lift before starting the placement of another lift. Okay, so this is important because if the structure is enclosed, okay, so if we don't do this, then after, if we just place the another lift of concrete, okay, so that will result in the cold joints. Okay, that is the segregation of both the layers because of the difference in water cement ratio. Okay, because a lot of water will be present upwards. Okay, so that will lead to segregation and difference in layers. Okay, spalling of layers. Okay, removing latents is very demanding. The placement of concrete should therefore not be suspended until the designated height or water surface is reached, unless suspension is inevitable. So here, because there is no issue of heat liberation, okay, heat of hydration or heat liberation, so it's better to, better to, as much as possible, better to cast the concrete at lesser lifts. Okay, lesser the lifts required, better it is. Okay, because otherwise you have to take care of the latents and all the segregation criteria. So in the case of a continuous lift of several meters, placement in short time may cause the form to swell due to the lateral pressure acting on the form and the mortar to leak. So one of the thing which is we have to take care in mind is that lifting and concreting at a very short interval. Okay, so continuous lifting of several meters in a short interval, that can lead to swelling and lateral pressure. Okay, which may result in which may affect the form, the concrete and the mortar. Okay, and that may lead to leakage. Okay, so due attention should be paid to the strength and assembly of formwork. In order to minimize concrete material segregation at the contact with water, the tip of the tremie or pump should be fixed during placement. Okay, so there should be no contact with water and the tip, the concrete. Okay, so therefore the tip should be inserted inside the concrete, this one fill. Okay, during placement it should be fixed. No bottom discharge buckets or bags should be used except for structures that are not so important, because they cannot enable continuous concrete placement, and the quality of concrete placed is not sufficiently reliable, because that is a very approximate method. Okay, very very old method, very inefficient method. Okay, the base method is basically through pumping or tremie. Okay, so tremie pipes shall be watertight and shall be uh, you know sufficiently large to enable the free flow of concrete. Okay, 25 centimeter inner diameter tremie pipes are frequently adopted where water depth is 3 meter or less, or 30 to 50 centimeter diameter tremie pipes are used where water depth is 5 meter or more. The inner diameter of the tremie pipe should be approximately 8 times the maximum size of coarse aggregate, Letting the concrete that flows out at the bottom end of the tremie flow in the water for a long time deteriorates concrete quality. As we discussed just now, the area where concrete can be placed by a single tremie pipe is generally limited to approximately 30 meters square. So it should not be more than 30 meters square. Okay, so basically that is the maximum uh, amount, okay, at one time. So this is a sketch, okay, representative sketch of how tremies are constructed. Okay, so they have enclosed, okay, so this is an enclosed structure through which concrete can be poured in, okay, and that is given through a scaffolding, okay, and these are the flange joints which connects this one, the structure, okay, and inside is the concrete, okay, so they have fixed it inside the concrete so that there is no contact between concrete and water, okay, so tip is fixed. Placement of underwater concrete by a tremie, as you can see. So underwater concrete is pumped to a lower area, so negative pressures are frequently created. The water in the vicinity penetrates the concrete and concrete quality is deteriorated unless the piping is watertight. Pipes of 10 to 15 centimeter diameter, 3 to 4 times the maximum size of coarse aggregate, are used in numerous cases. Area in which concrete can be placed by a single pipe is approximately 5 meters square. Okay? So contact between water and concrete, okay, uh, in the case of pumping, okay, contact between water and concrete in the pipe should be prevented by inserting a sponge ball, okay, at the start of concrete placement, and the pipe should be filled with water. The tip of the pipe should be embedded into the concrete already placed to a depth of 30 to 50 centimeter during placement for preventing the deterioration of concrete quality, okay. Pipe should be equipped with a check valve at the tip to prevent the reverse flow of water into the pipe or the underwater drop of concrete in the pipe, okay. Now that was all about concrete pumping. Now let us see about buckets, okay, discharging buckets or bags. So bottom discharge buckets and bags designed to open easily when discharging concrete as their bottom reaches the concrete placement surface, slowly lowered in the water during concrete placement. After the discharging of concrete, bottom discharge buckets and bags shall be raised gradually until they are fully away from the concrete surface. Causes the concrete to be piled and results in insufficient filling of the form. Therefore, water depth should be measured and the concrete should be placed at low points on the top surface of concrete. Okay, so these are some of the issues, because main issue is the precision and inefficiency. Okay, because it is a very traditional method. So that is basically all about the ordinary underwater concrete. Okay, now let us go through anti-washout concrete. Okay, so this is an underwater concrete. At the time of placement should have designated anti-washout capacity using the viscosity agents and fluidity sufficient to enable construction without compaction. Hardened concrete should have designated strength, durability and crack resistance. For providing these properties, anti-washout admixtures with designated capacity should be used. In the sea, alkali metal is supplied by the sea water in addition to alkali contained in concrete. Both fines and coarse aggregates should be safe in alkali silica reaction testing. Okay, amount of water content to obtain the required flowability is more than that of normal underwater concrete because of the increasing viscosity effect of the admixture. So because we have used lot of the viscosity agent, so therefore the amount of water required to achieve same flowability as compared to normal will be more. Okay, to avoid the excessive increasing of water content, high range water reducing agent shall be used at the proper amount. Some combinations with these agents and chemical admixtures for the resistance to segregation underwater may have a negative influence on the performance. Okay, the combination with admixture shall be examined thoroughly to confirm performance before use. Okay, so the anti-washout admixture, as you can see, for underwater concreting, so here there is with admixture and here without anti-washout admixture. So as you can see, in the case with anti-washout admixture or the viscosity agent, there is no segregation or latence. Okay, so it is a proper the integrity is maintained, proper integrity, the concrete integrity is maintained with sufficient amount of flow. Okay, viscosity modifying admixture to enhance the rheological or the flow properties of cement paste composed of microbial polysaccharides, gum or polysaccharide derivatives, for instance hydroxyethyl cellulose and hydroxypropyl methyl cellulose. Anti-washout admixture is substantially influential in enhancing the cohesiveness of concrete that is poured underwater. So basically the anti-washout or viscosity agent increases the cohesion, okay, so that there is less amount of segregation. Used for various structural construction, from small scale consolidation of rubble mounds to large scale bridge spire construction. Wide variety of types such as unreinforced concrete, reinforced concrete, and steel frame reinforced concrete. Mixed proportions should therefore be determined using tests fully considering the construction conditions such as the underwater flow distance, degree of flow, water pollution prevention, and underwater drop height, and the structural conditions such as the clearance of reinforcing bars so as to achieve designated strength, underwater resistance to segregation, fluidity, and durability. So these factors have to be kept in mind. Okay. 28-day compressive strength of a core sample of anti-washout underwater concrete placed at an underwater drop height of 50 centimeter or lower and an underwater flow distance of 5 meter or less is equal to or higher than the compressive strength of a specimen created underwater at the same age. The target strength of anti-washout underwater concrete shall be determined considering the design strength and variation of concrete quality. Okay. The underwater segregation resistance shall be determined based on the degree of underwater segregation or ratio between strengths in the water and the air. So all based on all these trial mixes, we have to find out the mixed proportions. Okay, the water cement ratio should be determined based on the results of check of chloride intrusion resistance. Okay, when determining the water cement ratio, considering the effects of corrosion on reinforcing bars and chemical action on concrete, the standard maximum ratio shall be determined as shown in table. Okay, so for fresh water, the water cement ratio will be 65% for unreinforced and 55% for reinforced concrete. Whereas in case of seawater, it is lesser, 60 and 50% respectively. Okay, for the durability, from the durability perspective. So as again, if we see the slump flow, okay, range, so we will see that in case where fluidity needs to be minimized, okay, such as in the consolidation of plastering on the surface of a steep slope or construction of thin slabs, okay, it should be between 35 to 40, lesser. Okay, in cases where concrete is placed in an area of simple shape, it can be little higher, 40 to 50 under normal conditions, and in cases where concrete is placed in standard reinforced concrete structures, it can be between 45 to 55. In cases where concrete is placed in an area of complicated shape, and in cases where high fluidity is required, it can be between 55 to 60. Okay. The air content, let us talk about that. It should the air content of anti-washout concrete should not be more than 4%. Okay, as a standard. In the case of excessive amounts of air, not only compressive strength is reduced, but also raising of air foam. Okay, in the concrete during concrete flow causes water pollution because it has a viscosity agent which is basically a chemical, and also quality variations may occur. Underwater concrete cannot be compacted in most cases. Okay, in order to increase concrete compactability, therefore the maximum size of coarse aggregate should not exceed 40 mm, and also not exceed 1 by 5 of the least dimension of a member, or nor 1 by 2 of the minimum spacing of reinforcing bars. Okay, so these are the factors to be kept in mind. Okay, for producing homogeneous concrete, cement aggregate and anti-washout admixtures should be dry mixed in a plant, and then water and designated admixtures should be mixed. Okay, so first cement aggregate, anti-washout admixture, they should all be mixed in a dry way, and then only water and some designated admixture should be mixed. Okay, the standard dry mixing time may be set at 20 to 30 seconds, just as we saw, 30 seconds of mixing dry, and then after adding water, 1 minute. Okay, at a ready mix concrete plant, the slump flow compressive strength of a specimen created underwater, ratio between strengths in the air and in the water, and the type and quantity of anti-washout admixtures should be determined. Okay, forced action batch mixers should be used in general. Okay, so these are some of the rules to be followed. Okay, as per the this one JSC code. Okay, anti-washout underwater concrete places heavier burden on mixtures than ordinary concrete. A batch should therefore be 80% of nominal. Yeah, because because of the segregation, because the viscosity agent. Okay, so it requires a heavier energy. Okay, for the mixing. Okay, as compared to ordinary concrete, and therefore the batch should therefore be only 80% of the nominal mixture capacity, but it should be not more than 80%. Okay, it should be lesser, so as to obtain concrete of designated quality. Okay, because more energy is required for mixing time should be determined only after conducting mixing tests to verify whether the concrete is of designated quality or not. The mixing time for forced action mixers is generally 90 to 180 seconds. Okay, so from 1.5 to 3 minutes. Placement. Okay, let us come to placement. Placing anti-washout underwater concrete is in water flowing at low speed or dropping concrete in water is likely to make reliable concrete. Okay, so concrete should be placed in static water. Okay, basically that is, as we found out, static water basically means the velocity should be less than equal to 5 centimeter per second at an underwater height of fall of 50 centimeter or less as a standard practice. Okay, concrete shall be placed either using tremies or concrete pumps. As I told you, this using bucket is a very traditional way, and that is not accurate, efficient, and also not a quality, not gives a quality mix. Okay, care shall be taken not to deteriorate the quality of anti-washout underwater concrete. That's why this one bucket should be avoided. Pump pressure is 2 to 3 times that for ordinary concrete. Okay, and the rate of pumping half to 1/3 of that for ordinary concrete. So anti-washout underwater concrete has higher fluidity than ordinary concrete. Okay, and causes little quality deterioration due to flow. Okay, area to be covered by a tremie or a fixed pump pipe may be increased over that for ordinary underwater concrete. Okay, the underwater flow distance should be held to 5 meter or less, because letting concrete flow excessively induces quality deterioration and heterogeneity. Okay, now let us come to marine structure. So structures that are in tidal areas, okay, or below the sea level and are subjected to the direct action of seawater. So basically these are structures which are in the shores. Okay, either offshore or onshore. So structures that are constructed on land or above the sea level and are subjected to the actions of waves, seawater, splash, those can also be called marine structures. So small members installed on the seashore, large marine floating structures, okay, large or deep sea marine structures, so all come into purview of marine structure. So general considerations, the measures shall be taken to prevent the quality degradation of marine concrete. Okay, structures during service life, okay, due to concrete deterioration or steel corrosion. Okay, concrete for marine structures, okay, shall be constructed fully considering the construction conditions, environmental conditions, and the effects of ships. Due care shall be exercised for environmental protection to prevent the pollution of the marine environment or the adverse effect on the ecosystem. Okay, the concrete is subjected to gradual damage due to damaging actions such as the physical and chemical actions of seawater, meteorological actions, and impact or friction caused by waves or drifting solids. Okay, chloride ion intrusion into the concrete is highly likely to corrode internal steel. In cases where concrete alone cannot fully meet the performance requirements, concrete surface should be coated to provide adequate protection in the marine environment, or epoxy resin coated reinforcement or other types of reinforcement should be used that are unlikely to be corroded. So all those factors need to be kept in mind. Okay, blast furnace slag, okay, that is the mineral admixture, or and fly cement are highly resistant to action of seawater, so they can be used. Portland cement with a low content of C3A is highly resistant to seawater. Okay, but that comes with a catch. Okay, that comes with a problem, that is low content of C3A will result in low capacity of resisting chloride and ions intrusion, and that will lead to accelerated corrosion. So in one hand it is highly lower C3A is highly resisting the seawater. Okay, and on the other hand it is not it is again increasing the chloride intrusion. Okay, it is not stopping the chloride ions, so that is resulting in accelerated corrosion. Okay, so there is plus and minus both together. Water cement ratio should be reduced to produce concrete with low permeability. So as we know, lower is the water cement ratio, lower will be the voids, okay, due to the evaporation of water, and that will due to the loss of water, and that will result in more lower permeability and greater strength. Okay, so yeah, so replacing cement with an appropriate amount of GGBFS or fly ash is important. Yeah, can be done. Watertight concrete highly resistant to chemical actions of seawater. Okay, so that will result in that, and also it will control chloride ion intrusion into our movement in concrete. Okay, so both is achievable using the mineral admixtures. And silica fume can also be used because it improves capacity of concrete for controlling chloride intrusion and resistance of concrete to seawater, and plus it is an ingredient used in HSC, high strength concrete. Okay, air entraining agents, water reducers, air entraining water reducers, high performance air entraining water reducers, that is the this one various types of chemicals, high performance water reducers and super plasticizers. Okay, so all those, okay, all those improve concrete workability, results in the production of highly durable and watertight concrete. These chemical admixtures provide high resistance to heavy meteorological actions and are fit for use in concrete for marine structures. Okay, so now let us see the anti-corrosives. Okay, what are the basic, because you know one of the this one of the main problems with marine, this one is the seawater seashore structure is the corrosion. Okay, so corrosion because of the chloride. Okay, so anti-corrosives applied to concrete surface coating or lining include organic materials such as epoxy, urethane and polyester resins, and materials mainly composed of polymer cement mixed with SBR or styrene butadiene rubber, acrylic and ethylene vinyl acetate copolymer. So basically all of these chemicals are used as epoxy, urethane and polyester resins. Okay, so some materials have not yet proved effective in actual structures over a long time. Quality varies greatly for one and the same material according to the construction condition. When selecting anti-corrosives, tests should be conducted or selection should be made based on the past examples of construction. Okay, embedded forms or permanent formwork using polymer impregnated concrete, cement concrete with synthetic resin impregnated into the voids are used as this one anti-corrosive. So various types of anti-corrosives are used. Okay, so this can help in reducing the chloride intrusion. So for the steel, okay, in cases where steel is subjected to cyclic loading, special care should be exercised to prevent steel corrosion as it greatly deteriorates fatigue strength. In cases where high tension steel like pre-stressing steel is used, subjected to stress exceeding 60% of tensile strength, the steel is likely to suffer stress corrosion. Okay, continuous fiber reinforcing materials have recently been used as non-corrosive reinforcing materials. Okay, so you know new technologies are coming where they are using fiber, okay, fiber reinforcements for non-corrosiveness of reinforcing material. So concrete, you know, concrete has this one members are likely to be subjected to various actions. Okay, so they are basically you know subjected to freezing thawing actions. Okay, in this one sea areas, chemical actions of various types of salt, basically chloride contained in seawater. Material deterioration and steel corrosion are likely to occur with the elapse of time, and in order to provide adequate resistance, water cement ratio, unit cement content and air content should be determined to meet the designated performance requirements. So all of this this are required, criterias are required to be satisfied. Okay, when constructing concrete under unfavorable conditions affected by seawater or tidal actions, the water cement ratio of the concrete should be reduced, okay, below that at ordinary construction sites. So the maximum water cement ratio, okay, that is determined from durability as per JSC is in offshore 45% for ordinary and 50 for special high quality. Okay, in splash zone it is 45 and 50, 45 same, and undersea also is 50-50 same. Okay, these are some of the criterias. Increasing the unit cement content produces homogeneous compact concrete and increases resistance to chemical intrusion, as we talked just now, of various types of salt contained in seawater and to internal steel corrosion. Okay, so minimum cement content, okay, that is dependent on the maximum size of aggregate. Okay, if it is 20 or 25 for offshore and splash zone, the minimum content is of cement is 330 kg per meter cube. For 40 mm it is 300 kg per meter cube. For undersea it is 300 and 280 respectively. Okay, so similarly there are standard air contents for concrete in marine structures. For offshore it is 5%, okay, for 20 to 25 mm coarse aggregate, and 4.5% for 40 mm coarse aggregate. Similarly in the splash zone it is 6% and 5.5% respectively. Okay, so with this we will come to the this one we'll finish the underwater concrete. Okay, so now let us go to one more special concrete today. This is the last. Okay, that is for this week. This is basically the roller compacted concrete. Okay, RCC. So as you can see here, this is nothing but the RCC, roller compacted concrete. And what is it all about? So concrete that is compacted by roller, okay, that is called the roller compacted concrete, RCC. It is, you know, the fresh concrete should be such that it is dry to the extent of being able to resist sinking of the roller and it is wet to the extent that the motor can be distributed within concrete during vibration. So it should not be too much dry, okay, so that it can resist the sinking of the roller, okay, and it should not be so much wet, okay, that it should be, it should be that much weight so that it can be distributed properly, and it should not be, it should not be so much dry that there is problem in the working of the roller, okay. So in between, where in between, the balance has to be made. The concrete RCC does is a very dry zero slump mix, okay. It's placed using dump trucks, okay, and compacted using a vibratory roller, okay. So these are the criterias, and basically it has two main functions, main construction applications. One is the dam and second is the pavement, okay. So dam and pavements basically use RCC. How we design the, how we make roads is nothing but through basically pavement. The concrete pavement is basically done through RCC, okay. So this one, the rigid pavement, basically it is nothing but the RCC. So applications, RCC is mainly used where large volumes of concrete is required, okay, and uh, so this one, it is mainly used where large volumes of concrete is required, with a further condition that it is largely unreinforced, okay. So RCC is basically used in unreinforced concrete, okay, and the two applications are, as we discussed, pavements and dams, okay. So prior to 1900, the large structure constructions like dams were not very organized, okay, because less information was there, okay. Between 1900 to 1930, okay, construction of dams such as Arrow Dam, Arrowrock Dam, Dalton Dam, Theodore Roosevelt Dam, so they were greatly accelerated because awareness started to build, okay. By the beginning of 1930, Hoover Dam was in the early stage of planning. We discussed this. Because of the exceptional size of Hoover Dam, investigations were much more elaborated than any other construction previously taken, okay. After 1970, roller compacted concrete was developed and became predominant method for placing mass concrete, okay. Roller compacted concrete pavements, okay, RCCP. So this is, as we discussed, a non-reinforced concrete pavement placed with high density paving equipment, okay. It is usually placed in layers of about 250 to 300 thickness, or about 1 feet. The layers are compacted with steel wheel vibratory rollers with final compaction, sometimes provided by rubber tire rollers, okay. So the aggregates, okay, the main composition is of aggregates, which constitute around 70 to 80% volume in RCC. It should have hard durable particles and should be appropriately evaluated. In the fresh state, they affect workability, potential to segregate, and ease of consolidation with a vibratory roller. Usually RCC mixes are not as cohesive as normal concretes, okay, and because the cement content is less, and thus aggregate segregation may be a consideration. Large aggregates reduce voids and thus the paste demand. So higher is the size of aggregate, lesser will be the amount of voids, okay, but the issue is of workability, okay. On the other hand, large aggregates pose a challenge in handling because there will be issue of compaction, spreading, and all those, okay. And fines add to the cohesion and contribute to filling voids and may be considered for use. So the spaces can be filled with fines, okay, and that will also add cohesion and contribute to void filling. So what are the types of cementitious material used in RCD? RCD means roller compacted dam concrete, okay. So any cement may be used, but from heat of hydration considerations, low heat cement is preferred, okay, because it is a mass concrete. The moderate heat Portland cement is used as the base material, and about 30% in mass of that could be replaced by fly ash, okay. The cementitious material content of RCD concrete is about 120 to 130 kg per meter cube, okay. This is as per JGC 18 standard specification dam concrete. So mineral admixtures, what are the various types? By replacing part of the cement in the concrete with admixtures such as high quality fly ash, temperature rise can be reduced without losing the required strength, and workability can also be improved, okay. It is common practice to replace part of the cement with mineral admixtures such as fly ash or GGBFS. The admixture fraction should be kept within the range in which the required earliest strength can be attained. The admixture replacement percentage is about 30% with fly ash and 50 to 70% with GGBFS. Okay, so these are the factors that can be used. These are the percentages by which the mineral admixtures can be replaced. Now let us go to chemical admixtures. The effectiveness of chemical admixtures is related to cement properties. Retarders may help to delay the setting time, which can help to have some time for compaction and prevent joint formation between the layers. But at the consistency of the RCC mixes, the real effectiveness is limited. Okay, retarding type air entraining agents are commonly used to disperse cementitious material and retard setting. In such cases, measured values of air content of freshly mixed dam concrete containing full size aggregate are often between 1.5 to 1%, okay, plus minus 1%. So around 0.5 to 2.5%. Okay, so the proportioning, how to proportion RCC mix. Okay, so there are two approaches. One is the approach which we use, the normal concrete approach, and second is the soil compaction. Okay, so basically it behaves as like the properties are very much similar to soil. Okay, so therefore we can approach it from the soil compaction way. Okay, so this uses principle of soil compaction to produce a dense mix where there is an optimum water content to produce maximum dry density, as we have we may have studied in soil mechanics. Okay, in geotechnical engineering, the amount of paste may not fill all the voids in the concrete. Okay, so these are the criteria. So basically we find the optimum moisture content which will give the highest dry density, and that is the highest compaction, and that will result in high strength. So this is one approach, using soil compaction. And the second approach, as I told, is using concrete engineering approach. Okay, so this is a traditional approach with a high paste content. In other words, the amount of paste exceeds the voids in the concrete. Okay, the functional parameters for design of concrete mix could be the compressive and shear strength, permeability, etc. This could also depend on the type of construction used. Okay, so and this in concrete we basically take the amount of binders even higher than voids. Okay, but in the soil compaction case, it is not like that. Okay, so there we try to find the optimum water content for producing maximum dry density, which ensures highest compaction. So because of the very low water content in RCC, mixing is not as productive using a central mix plant. Okay, so a pug mill is used, which requires a very high energy in mixing. Okay, it is important to control the moisture content, which is a critical component as like in soil. So even a slight overdose is too much and the roller may begin to leave marks. Okay, so it can be so much that it leaves marks. Okay, and it can be so low that it is not able to mix properly the mortar with the aggregates. Okay, so roller selection, some of the considerations that govern selection of a roller for use in RCC construction could be ease of maneuverability, compaction force, drum size, frequency and amplitude of vibration, operating speed, etc. Maintenance costs and ease are also important. The roller should be compatible with the size of project, workability of concrete, lip depth, extent of consolidation, space limitations, etc. as per ACI. Okay, and various terms are various parameters are coined. Okay, for example, the actual double amplitude. So this is measured under operating conditions, which will vary with conditions of material being densified and vibration frequency. So this is total peak to peak vertical movement, that is from normal position to peak above and normal position to peak below. So both from here to here and here to here. So it is total peak is the vertical movement peak is per completing vibrating cycle is the this one actual double amplitude in freely suspended condition. Okay, and that is basically the twice of nominal amplitude, which is taken only from here to upward. Okay, means a rest position to upward, not both. Okay, so this, as I told you, so drum movement, if you this is the rest position from here, if you have taken only the upward amplitude, so that is the nominal amplitude, but if you have taken both, okay, as here they have taken both. Okay, so it was here basically initially midpoint, then it has gone up and it has gone down, so total it is double, actual double amplitude. Okay, so nominal amplitude, it can be, the formula calculation is eccentric moment, okay, which is basically the suspended weight into the distance from the center of gravity divided by the vibrating mass, okay, which is basically the unsuspended, okay, unsprung weight, okay, which is just vibrating, okay. So about thickness, only a certain thickness can be effectively vibrated with a certain equipment. The extent of compaction achieved is related to the weight and other characteristics of the roller and the number of passes. Normally the thickness used in is about 300 mm, but it is a critical parameter from the viewpoint of the in situ properties of concrete and quality control. On one hand, there is a relationship with the maximum size of the aggregate used, whereas on the other it is related to the type of vibratory, okay, vibratory steel wheel equipment used, okay. So the thickness and the compaction, it is not only related to weight but also to the number of passes, okay, and also it may depend to maximum size of aggregate and other prior criteria, okay. So concrete properties, the fundamental rules of concrete, normal concrete apply with some modifications. With little water to begin with, there is practically no bleed water and less shrinkage than in conventional concrete, okay. So properties such as creep, coefficient of expansion, specific heat and conductivity are strongly determined by the properties and proportion of coarse aggregates used, because they occupy 70 to 80% of volume. Permeability of concrete is sometimes a critical property, and that could vary over several orders of magnitude in a construction given the method of construction, okay. The compressive strength is related to water cement ratio in conventional RCC, but is sometimes shown in relation with the moisture content, okay. So basically strength is related to W by C ratio as per Abrams law, but in case of RCC it is also related with moisture content, okay, because it generally it follows the soil compaction approach in a much more way, okay. Because there we find the optimum moisture content, which gives the maximum dry density, and that will give the highest compaction. Compressive strengths of course obtained from Canadian projects after several years of service uh, show that they are normally between 25 and 35 megapascal, okay. So this design gives strength around 25 to 35 megapascal. So vibrating hammer has been used to prepare RCC cylindrical samples, okay. So this is for testing as per ASTM C1435, okay. The flexural strength, it is between 2.5 to 7.5 megapascal, okay. But there is a difficulty of obtaining the the beam specimen which is cut from the actual site, okay. So sawing is difficult, so that's why it is little difficult for testing. And in case of split tensile strength, the tensile strength is an important property in pavement construction. But however, some researchers are of the view that in RCC strength should be determined using split tensile, okay, of course, rather than beam flexural type specimens, because of the problem of gathering sawed beam specimens from the actual pavement sites, okay. Bond strength, strength at the interface of RCC lifts is a critical property and will determine whether or not the RCC construction will behave monolithically, okay. So that's why this latence thing is a very important criteria, so if done in multiple lifts. So preparation of casting in terms of this one, in terms of spreading mortar, okay, surface preparation etc could also be carried out to enhance interlayer boundary, okay. So various preparations can be done for enhancing the interlayer bond. Then the density, okay, in certain cases this value could be a part of the specifications for RCC. It can be measured in situ using a suitable device. Using a mock-up trial, the minimum passes of a roller may be determined. Effort should also be made to relate the density measured to that obtained using cores etc, and finally to the compressive strength of the concrete, okay. So measuring density of RCC using gamma densitometer has been shown here, okay. So various techniques are used for measuring the density. And during compaction various problems arise. So here are a list of problems such as mixture tends to segregate, wavy surface during compaction, required target density not achieved, honeycomb surface, RCC tears during compaction, rock pockets observed, surface revealing, okay. So these are mainly caused by these factors: roller drums are not clean, vibration applied early, variable compaction speed, insufficient compaction effort, compaction is delayed, mix not ready for compaction. So all those take a all those play a big role in the problems, okay. And as you can see here, some of the designs, okay, after trial mix for various projects in Japan and USA have been shown in RCC. Okay, and yeah, the density ratio basically, okay, it can be seen as a function of vibration energy. Okay, so more is the vibration, roller vibration, okay, better will be the density ratio, which is self-explanatory, and it shows a linear curve. Okay, it is linearly proportional, and the vibration energy can be found out using a formula which takes into account amplitude, axial load, centrifugal force, travel speed, contact length between and concrete surface, frequency, passes of roller, drum width, etc. And density ratio is nothing but the density of concrete core by theoretical maximum density of compacted concrete. Okay, so we can find a relation. So yeah, lastly we will find out the various terms and definitions which have been used. So firstly, centrifugal force, it is given in kilonewton, and it is basically the force generated by the this one vibration, okay, inducing mechanisms at the stated frequency. Okay, ballast weight is the material added to increase the weight of the machine in kg. Drum is the rotating cylindrical membrane used to transmit compaction forces to soil or other surface materials. Dynamic force applied, so the vectorial resolution of all the generated forces and the static forces at the interface of the drum and the material being compacted. Okay, so frequency in hertz, it is a number of uh, completed cycles of the vibrating mechanism per unit time. Operating weight, it is in kilograms. The gross machine weight, okay, which includes the mechanical operating systems. Okay, the gross, the total value of full fuel tank, ballast, one half sprinkler tank, and also the person who is operating. Okay, say 75 kg operator. So all those is the operating weight. And non-vibrating mass, which is basically the spring weight. So this is basically causing the eccentric moment. Okay, so the static weight measured at the drums on the ground minus the vibrating weight. Okay, so that is the this one, the eccentric weight. Okay, and the vibrating mass, it is the basically the this one, uh, the unsprung weight. Okay, so that is the weight which is this one, which is the center of gravity. Okay, so the mass of all the intentionally vibrated parts at each drum. Okay, so using both this we get the amplitude. Okay, then vibratory roller. Okay, vibratory roller, uh, here next term comes the resonant frequency. As we all know, this is the frequency at which the drum and material will exhibit the greatest amplitude. Okay, so that is possible when the generated frequency coincides with the natural frequency of the material being compacted. Okay, so that is the resonant frequency, and this is the eccentric moment, as I told you. So it is the product of the unbalanced mass, or the sprung weight m times the distance r from the center of gravity of the unbalanced mass. Okay, to the bearing center. So bearing center is basically the unsprung weight. Okay, so if we divide, we get the basically the if we divide the sprung weight this into the distance between the center of gravity to the mass, and divided by the balance unsprung weight, we will get the amplitude. Okay, so with this we come to the lecture, end of the lecture. Okay, and we will go through some basic problems, and thereby conclude our lecture for today. Okay, so first question is, a fresh concrete pour with large surface area to volume ratio is more susceptible to thermal cracking. Is it true or false? Okay, and secondly, the temperature on the outer surface of the concrete is lower than that of the inner core due to dissipation of hydration heat in the atmosphere. Okay, so if the surface area is high, so liberation will be more, and if that is more, the concrete is less susceptible to thermal cracking, so one will be false. Okay, and temperature on the outer surface is lower than inner core due to dissipation of heat of hydration in atmosphere, so that is correct. So one is false and two is true. The second option is the correct one. Okay, so as you can see, second option is correct. Second question, in the context of mass concreting, which are the correct statements? In mass concreting, lower fineness cement with slow rate of hydration is preferred. So this is true. Lower fineness means increase in size, so that will reduce the rate of hydration and rate of reaction. and so that is preferred for lesser heat of hydration, liberation of heat. So one is true. And the cement content should be high in mass concreting procedures to compensate for low heat of hydration. That is completely false. In fact, it is the opposite way. Okay, so it should be less, so in order to reduce the heat of hydration, not to increase. Okay, so one is true and two is false. Okay, so that is the first is the correct option. Okay, then third question, in the context of mass concreting, consider the following statements. In mass concreting, the pre-cooled materials are used with the intent of lowering the placement temperature of concrete. And statement 2, the process of running cold water in a network of pipes buried in concrete is one of the post-cooling methods used to remove the heat generated and reduce temperature rise. Okay, so both the statements are correct. Okay, the pre-cooled materials are used for lowering the placement temperature, and the running cold water pipes, okay, buried in concrete, are used for post-cooling and removing the heat generated and reduce temperature rise in concrete. So both statements are true. So therefore, third option is correct. Okay. So fourth question, which of the following is not recommended for mass concreting? Okay. So use of higher coarse aggregate. Okay. Use increasing the coarse aggregate content. Okay. Replacing a part of cement by fly ash, or use of accelerating admixtures. So use of higher coarse aggregate is good because of the reduction of cement. Increase in coarse aggregate content is also important, so that will also reduce. Replacing a part of cement by fly ash is also good because that will also reduce the heat of hydration. But use of accelerating admixtures will add to the heat. Okay, so this fourth option is the correct option. That is, we don't recommend use of accelerating admixtures for mass concreting. So that is the correct option. Fifth question, which of the following cannot be used for underwater concrete placement? Use of concrete pumps, use of tremie pipe, use of bottom discharge buckets, or shotcreting. So concrete pumps are used, tremie pipes are used, bottom discharge buckets are traditional methods used, but shotcreting is generally done in hollow structures. Okay, so if it is used in underwater, it will lead to segregation and other problems. Okay, so it will just float because there is no this one, the weight will be less and more segregation and latence. Okay, so that's why fourth option, that is shotcreting, will be the correct one. Okay, sixth question, in the context of underwater concreting, consider the following statements. Statement 1, the anti-washout concrete uses viscosity agent to reduce segregation and bleeding of concrete underwater. Okay, and anti-washout concrete has more material cost, but the overall cost of using this concrete is lowered compared to that of ordinary underwater concreting. So both are correct. Anti-washout concrete uses viscosity agent, okay, for reducing segregation and bleeding, and anti-washout concrete has higher material cost, but overall cost is much lower. It is 80% if you remember correctly. So this one, both are true. So third option will be the correct. So yes, both statements are true. Seventh question, in the context of underwater concreting, consider the following statements. Underwater concrete cannot be compacted and hence requires an appropriate amount of fluidity. So this is correct. One is true. And statement 2, underwater concrete should be cohesive to minimize material segregation. Yeah, that is also true. So because of that purpose only, we use anti-washout or viscosity agent. So both 1 and 2 are true. So both statements are true. So third option is correct, as you can see. Eighth question, in the context of underwater concreting, consider the following statements. Statement 1, in underwater placement of concrete by tremie, the contact between water and concrete is prevented by covering the tip of the tremie pipe with a cap or inserting a plunger at the start of tremie placement. So yes, that is true. So our idea of this one to reduce segregation quality is by not allowing any contact between concrete and water during placement. So one is true. And 2, underwater concreting should preferably be done using bottom discharge buckets where more precision is required, in pouring the concrete. So this is false. Okay, so bottom discharge bucket should be least used. Okay, and that should only be used in if the structure is not important. Mainly we should go for pumping and this tremie pipes. Okay, so 1 is true and 2 is false. So first option is correct. So yeah, statement 1 true and 2 is false. Ninth question, in the context of roller compacted concrete, consider the following statements. Statement 1, roller compacted concrete is used in the construction of dams and pavements, and it is a relatively stiff mix of aggregate, cementitious materials and water, which has a consistency similar to zero slump concrete. Okay. And statement 2, roller compacted concrete is more cohesive compared to normal concrete. Okay, due to this one, low water to cement ratio. Okay, so first statement, okay, this is true. Okay, it is a method of construction of dams and pavements and relatively stiff mixture of concrete, aggregate materials, cement materials and water. Okay, which has a consistency similar to zero slump. So one is true. And roller compacted concrete is more cohesive. So this is false. Okay, because there is less amount of binding. Okay, cement content. And if less is the content, so this one, lesser will be the cohesive this one property. So one is true and two is false. Okay, so first statement is true. And last question, in the context of roller compacted concrete, okay, RCC, consider the following statements. Statement 1, it is recommended not to use retarding admixtures in RCC as they could result in the formation of coal joints. So statement 2, the amount of compaction achieved depends only on the weight of the compaction equipment. Okay, so yeah, so statement 1 is not correct, because in RCC we are, it's better to use retarding admixture because it is a mass concrete. Okay, so if we go for acceleration, then accelerated heat of hydration, so that will result in cool joints. Okay, so because of the heat liberation and the thermal stress. Okay, so that will result in thermal strength, thermal stress will be more than thermal stress, as thermal stress will be more than strength, resulting in cracking. So that's why the coal joints are formed. So it's recommended to use retarding admixture. So one is false. And second question, second statement, the amount of compaction achieved depends only on the weight. So that is also incorrect, because amount of compaction will depend on the weight as well as the number of passes. Okay, number of passes of the roller compaction equipment. So therefore we can say that both the statements are false. Okay, so D option is correct, fourth option is correct. So as you can see, both statements are false. Okay, so with this we have come to the end of the today's lecture. Okay, and basically here we have studied the heat of hydration and how the thermal stress affects the quality of concrete. And then we have got into special concretes. uh, One is the underwater concrete, where we have gone into there, where there are also three types. Okay, anti-washout concrete, standard under an ordinary underwater concrete, and marine concrete. So all of them are having their special criteria. And second concrete, we went for RCC, which is a roller compacted concrete. We found that it is used in dams and pavements, and it requires a lesser water cement ratio, and the water should be maintained so that uh, it can be sprayed. That much water is required, which is capable of mixing the mortar with the concrete during rolling, but it should not be that much so much that the roller itself gets sinked, or some marks are left after rolling. Okay, so that is our roller concrete. And there we saw that the design considerations can be done both traditional concrete engineering way as well as soil compaction way. Okay, so where we go for moisture content. And with this we come to the end of this week's lecture. So yeah, so if you have any question, you can ask, or else we can sign off. So okay, with this we come to the end. uh, Goodbye, let's meet next week.